Hello. So today we are going to learn about the method of separation of variables and the homogeneous method of solving a differential equation. So these two methods, they are actually the very basic methods of solving differential equations. So what exactly had we learned in the past few weeks? Okay, in the past few weeks, in my videos, you see that we had learned about solution of differential equations. We had learned how to form differential equations. Okay, and we had learned that there are three types of solutions: the general solution, the particular solution, and the singular solution. But how exactly do we find those solutions? It is by doing these methods. All right, so over here we will restrict ourselves to first order differential equation. That is, the derivative, it's of order 1. Okay, there are no second order derivatives or third order derivatives. Okay, so we will be dealing only with first order differential equations. This is actually kind of a map how to solve first order differential equations. The first method is the separation of variables. If that doesn't work, okay, maybe you will try it with homogeneous. Again, if that doesn't work, maybe by some substitution, we can convert it to a homogeneous differential equation. Again, if that doesn't work, we will convert it into, we will check whether the differential equation is exact or not. And if that doesn't work, we will convert it into exact. All these things we will learn in this semester, but for today, we will restrict ourselves to these two very basic methods: separation of variables and homogeneous method of solving a first order differential equation. Okay, so let's see. Okay, so first order differential equation, okay, because separation of variables, because since it is a differential equations of first order, okay, let us say that we have only two variables, x and y. What exactly will we do over here? We will write the term containing y on the left hand side. We will write the term containing x on the right hand side and then simply integrate. Okay, so this is exactly what we will do. Write the terms containing y on the left hand side and the terms containing x on right hand side. Okay, so if you can do this, if this can be done, then we proceed to step 2, which is integrate. All right, so this is what we will do. Okay, I will highlight this one with an example. So let's see. Solution. Okay, maybe solve. Whenever we are asked a question to solve, it means we have to find the general solution. Okay, solve. All right. X, y plus x dy plus xy plus y dx is equal to 0. Okay, so if you notice this one, it is actually a first order differential equation because we are having only first order derivative. Okay, as you shall see. Okay, so what I will do over here, we can write it in this way. We can take common x, y plus 1. We can take common y, x plus 1. So this is what we will do first. Okay, first we will keep dy on the left hand side. Okay, if you take this one to the right hand side, we'll be having this dx, right? So now what can we do? If you take a look at the rule, all terms containing y on the left hand side. So this is a term containing x, we will have to take it to the right hand side. And this is containing y, so we'll take it to this side. Y plus 1 upon y dy minus x plus 1 upon x dx. Okay, so this is what we achieve. Okay, so if you notice now the left hand side, it contains only y and the right hand side contains only x. So So separation of variables has been done. Okay, we had separated the variables into y and x. Okay, so the variables are separated. So once this is done, now we will integrate. Okay, so if you notice that differential equations, if we solve them, it will involve integration. So you need a very strong concept of integration as well. At least the methods of integration you should be familiar with. Okay, so how will we integrate this one? We will split the fraction. Okay, and over here we'll be having dx. And over here we'll be having y, log y, minus x, minus log x. Okay, so over here what shall we do? Okay, there are two terms containing logarithms. So remember that if we integrate, there will be a constant of integration. We can write it as c, or we can write it as log c. Okay, it is entirely your choice. You can choose whichever you like. Either you write it as simply as log c, or you write it as log c. Okay, so we can, okay, maybe it's best if we write only c. Okay, so we can take this one to this side. Okay, keep the logs on one side. In fact, okay, you can even end the solution over here. Okay, but we can simplify further if you wish. Okay, log yx equal minus x plus c. Okay, so this is the required solution. General solution. Okay, so whenever we are asked to solve a differential equation, we will first have to find the general solution. The particular solution will involve something else in the question. Okay, so separation of variables is an easy method. That is why I am doing only one exercise. Okay, now let us go to homogeneous, the second method, which is the homogeneous method. Okay, again I repeat, you don't need to do homogeneous method if you can do it with the first method, that is separation of variables. But in case the variables cannot be separated, then you will have to resort to this theory of homogeneous differential equation. Okay, first order differential equation can be written as m dx plus n dy is equal to 0. Okay, as we had seen in the previous example. And it contains only one derivative, that is why it is a first order differential equation. M and n depends on x and y. Okay, the equation above is homogeneous if m lambda x lambda y equal lambda n mxy. Okay, you will see what this definition means. It's homogeneous of degree n. If n lambda x lambda y equal lambda power n xy. Okay, so this is not the method. Okay, this is just when to check. Okay, how to check that a differential equation is homogeneous. So we will have to do this. Okay, example. Okay, check that the equation okay, let's see, x cubed dx plus y cubed plus xy square dy is homogeneous. Okay, so m dx plus n dy equal to 0. Okay, we have to check whether it's homogeneous or not. So solution, okay, we can write this one as m, this one as n, it doesn't matter. So over here we are getting m x y. So this one is m, it depends on x. Okay, so similarly n xy, it's equal to y cubed plus xy square. So this one is n. What happens if we replace xy by lambda x and lambda y? Okay, so over here, if we replace x by lambda x, we'll be getting lambda x whole thing cube. So we will be getting lambda x, lambda cube, x cube. But x cube, it is mxy. Okay, similarly over here, let us replace it with lambda x and lambda y. So over here we'll be getting, instead of y, you will be getting lambda y. X, we have to replace it by lambda x, and y by lambda y. Okay, so we'll be getting lambda cube, y cube. Again, over here we'll be getting lambda cube, x, y square. We can take common lambda cube. Okay, y cube plus x, y square. So we notice that this one is actually lambda cube and xy. Okay, so this one is equal to this one is equal to this. Lambda has been raised, both of them power 3. Okay, so that is why it is homogeneous. Is homogeneous of order of degree, the degree lambda power 3, so degree is 3. Okay, in case over here you are getting lambda square and over here lambda cube, then it is not homogeneous. If it has to be homogeneous, then the power over here should be the same. Okay, 3 and over here 3, or 2 and 2, 1 and 1, 4 and 4. Okay, so if lambda has the same power here as well as over here, then it will be homogeneous, and the power, it will be the degree. Okay, but how to solve a homogeneous? Okay, number 1. Okay, so if it is a homogeneous equation, this is what we will usually do. Express it in this way. Dy dx is equal to something. Okay, let it be anything on the right hand side. Okay, but the left hand side, keep it only as dy dx. Okay, then perform a substitution. Y equal vx. Okay, when you perform the substitution here as well as here, it will be, then you can separate the variables. All right, so when you separate the variables, you will have to integrate. After integrating, remember that the final solution will be in terms of x and y. So you will have to use v, it's equal to y by x. Okay, use it, this one again. Okay, that we are using the substitution, so we will have to convert it back into y and x. So this is what we will do. All right, so but this method can only be used for a homogeneous differential equation. But you notice that when we have to check whether it is homogeneous or not, it is actually quite tricky. Okay, because we will have to involve lambda and everything. Okay, that can be skipped. That can be skipped. And over here you notice, okay, the right hand side will no longer contain a derivative. But what happens if you substitute this one in the left hand side? Dy dx, it will be d dx of Vx, okay, you can use the product rule, you'll be getting this V plus X dV dx. Okay, so the left hand side can be replaced by V plus X dV dx. Okay, keep this in mind. All right, but how exactly do we detect a homogeneous differential equation? Okay, because using lambda will take a lot of time. So this is what I usually do. Okay, in fact, all of us do it. How to detect a homogeneous differential equation. Okay, suppose you are just given a random differential equation. Okay, it's equal to 0. Okay, firstly, it has to be of this form, mdx plus mdy equal to 0. Okay, now just check the powers. The combined power of x and y. X is of power 2, right? So this term contains power 2. Similarly, this one contains power 2. This term contains power 2, right? So all the powers are 2, so that's why it will be homogeneous. Okay, let us use another example, maybe xy dx, xy plus x squared dy. Again, it is of that form. X, it is of power 1, y, it is of power 1. So the combined power is 2. Similarly, over here, the combined power of x and y is 2. And this one, again, the power it's 2. Again, homogeneous. And the degree, because it is homogeneous, power 2. Again, okay, let us see another one. Xy plus 1 dx equal to 0. Let us see whether this one is homogeneous or not. So the combined power over here is 2, whereas the combined power over here is 0. Right? X power 0, y power 0. Okay, so over here only, you see that the powers are no longer the same. So that's why this one, it is not homogeneous. Okay, so just by checking the powers, we can easily detect whether the given equation is homogeneous or not. All right, so with this being said, let us solve a differential equation, okay, which is homogeneous. Okay, so the question is solve. All right. Okay, so solve. Let's see. X squared 2xy dy minus x squared plus y squared dx, it's equal to 0. Okay, so we can easily detect that this one is homogeneous. The power over here it's 2, the power it's 2, the power it's 2. So indeed it is homogeneous. Okay, maybe I will add some more to the question. Also find the particular solution. When x it's equal to 1, y it's equal to minus 1. Okay, so let us see. X equal 1, y equal minus 1. Okay, so since it is homogeneous equation, now we just need to follow the steps. Okay, firstly, okay, we will get like this. You notice over here that the variables cannot be separated. Okay, no matter what you try, the variables cannot be separated. Okay, you cannot take this x over here because y, it will always combine with dx. Okay, so the variables cannot be separated. That is why we are resorting to homogeneous differential equation. You notice that this one can actually be written in this way. Okay, so this is what we will get. All right, so this is what we will get. let's see. So over here, x squared plus y squared upon 2xy. Okay, so now that we have written it in this way, so we have completed with the first step. Now let y equal vx. Okay, let's substitute y equal vx. So if you differentiate y with respect to x, okay, you will be getting v plus x dv dx. Okay, and over here x squared, over here y squared will be v squared x squared, 2x, and over here y, it will be vx. Okay, again we can write it down. So you will be getting x squared 1 plus v squared, and you'll be getting x squared 2v. Okay, so this is what we are getting. Okay, maybe let us make the question a bit easier. All right. Okay, how will we make it easier? Okay, let us do it first, this one, okay, without any 2. Okay, it will in fact be simpler, I feel. All right. Okay, now after doing this, we notice that x squared can be cancelled. So since x squared can be cancelled, so we'll be getting v plus x dv dx. It's equal to 1 plus v squared upon v. Okay, so that is what we are getting. Now we need to separate the variables. We had done the substitution. Now we need to separate the variables. So keep v first on this side minus v. Okay, so this is what we are getting. Okay, firstly, let us try to separate the variables. So you'll be getting this, right? So this one and this one again will get cancelled. 1 upon v. Now separate the variables. dv keep it in this side, and dx keep it on that side. Okay, so this is what we are having. So after separating the variables, we can integrate. Okay, after integrating, this one will become v squared by 2. Integrate this one will become log x, okay, plus c. Okay, but remember that y was equal to vx, so v will be equal to y by x. So similarly over here, substitute it back. V is equal to y by x, so we'll be getting y squared by 2x squared equal log x plus c. Okay, so this is in fact the general solution because it contains an arbitrary constant. Okay, so this is the general solution, but we need to find a particular solution. Now, when x equal 1, y equal minus 1. Okay, substitute it over there. Y squared will become 1, 2x squared will become 2, log 1 will become 0 plus c. So c, it will become 1 by 2. Okay, substituting in 3. Okay, we will be getting y squared by 2x squared equal log x plus 1 by 2. Okay, so this is in fact the particular solution. Okay, so this is the required particular solution. You notice that it is called a particular solution because the value of c now has a particular value, that is 1 by 2. Okay, so this is how we do separation of variables, and this is how we solve homogeneous equation. Until next time.